Hello everyone, welcome back to the course on materials informatics. Today we will talk about a simple regression workflow. So just to provide a recap of what we discussed in the last lecture, we spoke about some use cases of machine learning which can actually help humans in solving more complex problems. We also discussed several types of classifying machine learning systems, right from the type of output they predict, how much human supervision they require, whether they learn in batch mode or online mode, so singular data, whether they memorize all the data or try to learn some fundamental mathematical relations or equations, and how complex the models are. We also discussed a few other terminologies such as datasets, features which are used to uniquely identify each data point in your dataset, parameters and hyperparameters associated with models, the specific algorithm you generally use to fit a model or to train a model, and also the objective function. So what is the model trying to minimize or maximize as it is learning from the data that it is seeing, and the importance of scaling as well. So we generally need to scale our features and sometimes even our target variables. And we also discussed some of the common issues such as complexity of the model, the trade off between over and under fitting, and also issues related to data. So in this lecture we will focus on a simple regression workflow, and once again all the schematics that I am going to be presenting are part of this book by Aurélien Geron. Okay. So what is a simple regression workflow? So first is we have to frame the problem. So what is it that we are trying to learn or predict, and then second is we have to get the data. So for this workflow we will use an open source data set that we are going to use, but sometimes you may need to generate this data manually as well. So this may be more time consuming than you anticipate. And the third thing which we should typically do is to visualize the data, and a lot of the times visualizing the data often gives us insights and helps us choose the right model. So it helps us ask the right questions, and we also should try to understand the features. So how is it that we are characterizing every data point that we are actually feeding into our model? Are the features actually relevant? Should we introduce new features and so on? And then we have to prepare the data for machine learning. So sometimes we have to clean the data set that we have obtained, and a lot of the times we have to ensure that the data is scaled, right. So it is either normalized or standardized or both. And finally we have to select a model and train, and then we try to improve our model. So basically fine tune our model's performance, and this is usually an iterative process. And finally when we are happy with the model, we either present the model to others who are interested in the model, or we deploy the model for practical use cases, right. So we will go through this entire workflow, but in this lecture itself we will probably focus on the first 3 tasks or so, and then the remaining tasks we will move to the next lecture. Okay. So the problem that we will try and predict or learn is the median house prices. So how expensive houses are in the state of California in the United States. This is a very nice sort of regression problem that we can begin with, and we are going to be basing that on the sort of census data that came out of the US in 1990. So this is quite a sort of old data set. It's about 35 years old now, but it is a very nice problem to learn how to do simple regression. Of course this problem is not really a material science problem, so we will focus on regression tasks associated with material science in our hands-on sessions, right. So just to give a sense of this plot, so this is a map of California state that is highlighted in yellow here, and these bubbles are all referring to different population sizes in each of those regions within the state, and the colors themselves indicate your median house value. So how expensive on an average houses are within a given area, right. And it is this median house value that we are going to try and predict with our regression models. Okay. How are we going to evaluate our models, right. So we will try to train a few models in this exercise, a few regression models, and each of those models we need to ensure that they are performing as good as they can be, right. So we will use two performance metrics. So one is the root mean squared error, right. So root mean squared error is often given as a function of your input features that you provide the model and the model itself, the model's parameters. So x here refers to usually an array of input features that you feed into your model. So these input features characterize each data point uniquely, and h refers to the set of parameters that are used to define your model. So this can be how the model is defined itself, so its functional form, and also some hyperparameters that are used to optimize the model, right. So typically machine learned models have this notation of h of x. So h of x is basically your predicted value by the machine learned model, and y is your target value, right. So we basically calculate the difference between our predicted value and our target value for each data point that we have, right, take the square of them and then sum up all the squares and take the average, right. So we basically divide by the total number of data points we have, and once we divide it and take the entire square root of it, we basically get the root mean squared error. So if we do not take the square root, we get the mean squared error, that is MSE. Root mean squared error is sort of more commonly used. And the reason why root mean squared error is commonly used is because it is intuitively what we refer to as distance, right. So let us say you want to measure distance between 2 points in a Cartesian coordinate space, this is how you would measure, right. So it is y1 minus y2 square plus x1 minus x2 square and so on, right. So this is how you typically measure Cartesian distance or distance in Cartesian coordinates. And often root mean square error can be sensitive to outliers. So if you have a few points that are being predicted very wrongly by a model compared to the rest of the points, your RMSE can dramatically increase, right, and if you remove those outliers, then the RMSE value can decrease quite significantly. So depending on how many points that are being dramatically wrongly predicted by your model, your RMSE value can change quite significantly. The other metric that we often use is what is referred to as mean absolute error, right. So this has a very similar definition to RMSE. The main difference is that instead of taking the square of the difference between individual predictions and the target values and then taking the overall square root, we take the modulus. So basically the absolute difference between your prediction and your target value, right. So we take the absolute difference in our predictions, or absolute errors in our predictions, and then divided by the total number of data points we have. So that is why we get mean absolute error here. So in some sense mean absolute error measures what is referred to as Manhattan distance in Cartesian space. So root mean squared error measures the linear distance, right, and mean absolute error measures the Manhattan distance. So the difference in the x coordinate and the difference in the y coordinates, and then you add them instead of taking the square and then taking the square root of it. So it measures the Manhattan distance, and nice thing about mean absolute error is that it is less sensitive to outliers. So even if your model has badly predicted outliers, whether adding them or removing them does not fluctuate the mean absolute error values significantly, right, whereas it can fluctuate root mean squared error values significantly. So we would be using both of these, both RMSE and mean absolute errors, to keep track of how our models are performing. Okay. So let us now go to the notebook, go to our Jupyter notebook here. We will first get the data, right, and then we will visualize the data. So see how the data looks like, what kinds of features it has, right, and then we will try to create a train test split of the data, right. So we will we'll download the entire data set, and then we will split that into a training portion where we will look to train our models, right, and then a test portion which will not be exposed to the model itself, and the test portion of the data set we will only be we'll only be using for verifying the performance of our best model, right. So that is the importance of creating this train test split to ensure that however we train our models, they have truly extrapolative capabilities on data points that they have not seen, right. So we will do this exercise. So let us now go to the notebook. In the first block of the notebook, basically we are looking at initializing or downloading a few important modules. So if you look at the first block itself, let me execute the first block. We ensure that there is a certain version of Python that is being used in our exercise, and we also ensure that scikit-learn has a minimum version, and we sort of define these matplotlib library definitions to ensure that we can plot the figures inline within our notebook itself, and they look reasonably presentable. And then we also define a project directory. This is to help sure that your files are organized as you keep executing different notebooks through your through the duration of this course, right. And we also define a save figure option here to make sure that our figures are getting saved, so that we can sort of look at them even after the notebook is closed down, right. So the first block is just basic definitions, and it is often useful to define such a block to ensure that your notebook is compatible with what you want to do, right. Okay, let us now go to getting the data part, right. So here there are again a couple of modules that we require. So OS is basically the operating system. Tar file is a module that helps us deal with zipped or compressed files within Python, and then URL library basically allows us to handle URLs within Python. So the data set that we are looking for, the California housing data set, is available in this GitHub repository here, right. So we are basically going to just download the data and then sort of extract the zip files, and for extracting the zip files we are sort of defining a fetch housing data function here, which we will be using to extract all the files. In case you have difficulties in following all the lines of code, do not worry. So we will go through some basics of Python in the first hands-on session that will follow after the regression exercises. So let me try to execute this block of code. So we have now defined where to get the data, and then we now have to execute this function to actually get the data. So now the data has been imported, and it is available locally on our computer here, right. And in the next block we are going to define or we are going to import this pandas library. So pandas is very useful within data science, machine learning in general. It is used as an organization tool, right, and it has lots of useful functions both for analyzing the data and visualizing the data, and many of the sort of machine learning modules work directly with pandas data frames, right. So it is a very useful tool to be aware of, and we will be extensively using pandas through the duration of this course, right. So let us now load our pandas. So basically we have downloaded the data and then sort of exported the data into a data frame, and in case you are hearing data frame for the first time, think of data frame as an Excel sheet within Python, right. So it is a sort of a programming Excel sheet that is available within Python itself, right. Okay. So now that we have loaded our data frame, let us now take a look at what data is there. So let us take a look at the structure. So we are loading up the data here, and this head function within a data frame basically summarizes the first few rows that you have within your data frame. So think of you as taking a zoomed look within your Excel sheet and looking at just the first 5 rows. Right. So if we now execute this, we see that there are lots of different features that are now being listed. So you have a longitude latitude feature that basically localizes the geography of a given locality or of a given house, right. And then you have a housing median age, right. So what is the average age of people, median age of people who are living in that house, how many rooms does the house have, right, or how many rooms in the overall locality do all the houses put together have, how many bedrooms in total do all the houses put together have, what is the total population of that locality, how many households are there, and what is the median income in that locality and median house value. There is also a column called ocean proximity that basically measures how close the locality is to the ocean itself. So California in the US is a little bit like Tamil Nadu or Kerala or even Karnataka in India, which has a coastline, right. So you can also measure how close a locality is to the coastline itself. And out of all these values the median house value is the target that we are after, and that is what we want our models to be able to predict, right. Let us also get a little more information about each column. So the housing.info, so housing is our data frame, the name of our data frame, .info is the function that we are executing, right. And once we execute we get a nice summary of all the different properties of the columns, right. So for example we see that longitude, latitude for example have about 20,000 rows, so each column has about 20,000 values and all of them are floating point values, so these are all numbers, right. Whereas ocean proximity for example is listed as object here, and that basically refers to the fact that it has text value or number, non-numerical kind of values, right. And there is also one specific column here called total bedrooms, and that only has about 20,400 rows, not 20,600 rows, so it has a few missing data points within that row, right. So these are sort of things that we should take note of once we look at a data set, right. Let us now for the non-numerical column, the ocean proximity column, let us see what type of values it has. So it turns out that it has 5 different values. So one is, it says it is less than 1 hour from the ocean, right, and there are about 9,000 localities that are less than 1 hour from the ocean. There are localities which are called inland, so they are far away from the ocean, about 6,000 of them, near ocean, so that is I suppose somewhere between 1 hour, less than 1 hour and the ocean itself. And then there is something called near bay. So near bay basically refers to the Bay Area in California, which is close to the city of San Francisco. So that has a specific tag associated with that, and then there are islands in the state of California, and there are 5 island localities, right. So this is what is contained in the ocean proximity column or feature. The dot describe function is often very useful in data frames, and this gives us a lot of statistics. So for example if you take longitude as the column, right, so it says that there are 20,000 data points in longitude. What is the mean of the data points, so average, right. What is the standard deviation, so the longitude does not vary by much, it only varies by 2 degrees. What is the minimum value, right, what is the 25th percentile value, 50th percentile value and 75th percentile value, and what is the maximum value, right. And we can get such statistics for all the columns that we have, right. So we can even get statistics for the target value that we have. So we see that the minimum is about 14,999 and the maximum is about 5 lakhs here, right. So those are the sort of target house values that we have, and we also see that this column called total bedrooms has fewer data points than the remaining columns, right. So this is something that we have to think about. So it is often the case that when you do or when you try to do machine learning or build machine learning models, you can have incomplete data sets. So you can have data sets which do not have all the features that you want, and in such cases you may have to use some strategies to ensure that your model does not break down completely, right. So we will get to those strategies a little later in this lecture or the next lecture. Okay, so let us now look at or try to visualize these data distributions as well. And this code block here basically generates a histogram for all of the features and the target value that we have. So you see that for households it generates a histogram, for households it generates a histogram of values, for median age as well. So you see one big spike beyond 50 here and then sort of a normal distribution below 50. You see latitude being distributed. This is for longitude, median house value, this is our target here, right, and then median income and so on, right. So for each of the numerical values we can generate these histogram plots, and it is often useful to look at and get some insights. Alright, let us now create a train test split, right. So one way to create a train test split is to use this function called train test split from scikit-learn. So scikit-learn is a machine learning library that we will use quite often in Python. It is very good as a starter sort of module to learn machine learning and also practice machine learning. It has access to a lot of simple our classical machine learning models. So it's quite useful, and we will be using that heavily in the first module of the course, right. So we will use this train test split, and the way the train test split works, the function works, is that you give it a size of the data set that you want in the testing testing subset, right. So what we are basically saying is that we have about 20,000 data points in total, and we want to reserve 20% of the 20,000, so roughly about 4,000 data sets as test, right. So that is the data that we are not going to expose to the models while they are being trained on, right. And this random state is basically to ensure that your train test split is random. So you are not taking the first 4,000 or the middle 4,000 or the last 4,000 data points, you are taking 4,000 data points at random, and this is often a good exercise to do in most data sets, because we do not want to bias our data set in one way or another, right. And the specific value that you give in the random state, that is basically to ensure that your exercises are repeatable, right. So you don't, so if you do not give a random state, each time you create a train test split, you are going to get a completely different distribution in your training and test sets, right. So if you want a random distribution, but if you want to repeat that random distribution, so say someone else wants to go through your same exercise, he or she should be able to repeat what you have done, you normally give a seed to that random state, and that ensures that your exercises are repeatable in nature. So we will use a random state seed of 42 here, okay. So once you execute, your data set is already split now into train set and test set now, and if you look at the test set itself, you see that it has all the same sort of columns, all the same features as your training set, right. So the training test set split was done properly, and test set seems to have all the data that your overall data set had, okay. Let us now go back to the slides, okay. So when we did the train test split, we initially did a random split of training and test data, but often it may be useful to do what is referred to as a stratified split. So what I mean by that is, so let us say you are in this specific example of median housing prices, maybe there is a strong correlation with with the average income or the median income with the median housing prices in a given locality. So if you think about it, right, so if on an average the people in a locality are richer, the housing price tends to be higher in that locality, and vice versa, right. So on an average, if people in a locality are poorer, then the housing prices tend to be lower, right. So if we do let us say a random split of our data set, maybe we are going to get a lot more data points from high income localities within our test set rather than low income localities within our test set, right, and that may unfortunately bias our model during training, and it may not be able to make good predictions on our test set, right. So in such cases, we can do what is referred to as a stratified train test split. So the main idea is that you split your data set into sort of 3 or 4 different bins of data points. So in our case, we can probably classify our data set into low household areas, medium household areas, and high household areas, for example, right. We can even sort of define subcategories further, so low to medium, medium to high, and high, right. So we can have 5 different categories, for example, of our 5 different income categories, and we can sort of classify our overall data set into these 5 different categories, right, and among the 5 different categories we choose we choose a number of data points within our test set at random corresponding to how many data points they have overall. So for example, if you have 10,000 data points which are in the low income category, 5,000 in medium and 5,000 in high, for example, right, and if you want to take 20% of all the data points into your test set, you take 20% of 10,000 which is about 4000, right, sorry, which is about 2000, and then you take 20% of 5000, which is 1000 data points, and then you take 20% of the 5000 in high income category, which is about 1000 data points, right. So instead of taking 4000 randomly across all the 3 categories, you take 20% in each category, right, and within each category you take data points at random, right. So within each you take data points at random, but you define how many data points to take from each bin basically, right. What this does is it ensures that your test set is very well represented, and your training set is also very well represented. So it gives a fair chance for the model to learn well and extrapolate to scenarios that it has not seen before. So for example, if you train the model only on low income households and do not expose it to housing prices on high income households, then the model, it's unfair for the model to make good predictions, or unfair to expect the model to make good predictions for the high income households, right. So that is where stratified split is often useful, and it is usually practiced also, especially in sort of data distributions that may be highly correlated in nature, or data distributions that are skewed. So let us say you have a lot of data points in in low income category and very few data points in the high income category, then it does not make sense to take a lot of data points from the high income category into your test set. So you should take proportional number of data points, right. So that is the main idea between random and stratified trained test split. So in the previous exercise we did random split, so we will look at how to do stratified split in our notebook. So let us get back to our notebook here. Right. So we are now looking at the median income. So the plot that you saw on the slides is basically the histogram of the median income, right, across all the localities, and you see that the median income is sort of distributed in a fairly skewed fashion, right. So there are some incomes that are more represented and other incomes that are not, right. So let us now try to categorize the income, median income, into 5 different categories. So I am going to sort of call 0 to 1.5 as one category, 1.5 to 3 as the second category, 3 to 4.5 as the third, 4.5 to 6 as the fourth, and 6 to basically infinite as the fifth category. And if you are in case you are wondering how can median income be sort of $14, right, it is basically a scaled unit. It is probably 14 times $100,000 per year, right. So that's probably the range that we are looking at. So it is definitely scaled data from what we see, but we can sort of categorize it into 5 bins, right. So so in this coding block we have already categorized our income into 5 different categories. Let us now see how the incomes are actually distributed, right, within our housing data set. So we see that the extremely poor and extremely wealthy are not that well distributed, are not that well represented. So they only contribute to about 4% and 11% of your overall data set, whereas the sort of middle middle income and slightly lower middle income, right, represent bulk of the data. So they represent about 35% and 31% of the data, and medium to high income is about 18% of all the data. So if you want to visualize this as a histogram, you see that so income category 2 and 3 are the most most represented in our data set. They are having about 6,500 and 7,000 data points here. The remaining are sort of more sparsely represented. Okay, so given the skewed nature of our data, let us now try to do a stratified test split, right. And luckily enough, scikit-learn already has a ready-made ready-made function or ready-made class to do stratified shuffle split. So what this does is it for each, so it is able to take data points from multiple categories, so multiple stratifications of your data, and within each category it will basically do shuffling and take data points at random, right. So that is why it is called a stratified shuffle split. Okay. So first thing you do is initialize the class. So you say how many splits you want. So we want one split. So one is training, other is testing. So that is one split of the data. And we sort of mention what is the size of test set that we are looking at. So we want about 20% of the data to be in the test set, and we also initialize a random state. So let me execute this block here. So the split function is what does the job, right. So we initialize stratified shuffle split class as the split class, and then it has a split function within it where we pass in the data set, and then we sort of indicate which category or which based on which feature we want to split the data, right. So we say that it should be split based on the income category feature, and income category feature is what we defined here, right, in the previous block, right. So income is one category, income category is a different category, right. So the split function does the job, and it already sort of splits into training and test sets. So what the split function does, it actually gives us the indexes or the row numbers within our data frame. So we basically have to collect all the row numbers and then assign them into our train set and test set, right. So that is what this locate function helps us to do, the lock function here. And then I mean there is also slight differences between ilock and lock, but for our purposes here you can use either of them, there should not be a significant difference. Okay, so let us now try to see what kind of statistics the test set has, right. So we are again looking at the income category column of our test set, and we are seeing what is the distribution, and we can also compare it with the overall data set, right. So we see that the stratified test set now has about 35% in the most represented category, that is category 3, which is actually similar to our overall data set, right. And same thing with category 2, category 4 is also similar, category 5 is also similar, and category 1 is also similar. So we see that the stratified test set has very similar statistics, right, compared to our overall data set itself. Okay. We can also now compare the differences between our random way of splitting our data set and the stratified way of splitting our data set. So this block basically defines a function which helps us do that. Do not have to worry about the details, right, but basically what we are trying to do is to do the random train test split, and in the random test set see the statistics according to the income categories, and in the stratified train test split see the distribution according to income categories and see how these distributions are different, right. So if you now compare the properties, we see that random distribution per se is not that bad, right. So I am looking at the percentage error columns here, right, in the output. It is not particularly bad, but the stratified test split is better, it is indeed better than the randomly split data sets, because all the errors compared to the overall data set distribution are all below 1%, right. Whereas in the random distribution you have about 4% errors and so on, especially in the sparsely represented data sets, right. Okay. So the final thing that we have to do is ensure that we clean up our data set. So we define income categories only for defining our stratified train test splits, right. We do not need that anymore for building our models. So we are going to drop that from our data sets, from both the training data sets and the testing data sets. So let us now get back to the slides. Okay, so now that we have created train test splits, let us now look at the data, and often visualizing the data is quite important, especially when we do supervised learning. So we are supervising our machine learning models, and especially when we are creating simpler models which have a lot of physical intuition. Because when we train simple models, it is often human intuition and human sort of guesses that help us identify or construct better models than models that do not have human supervision or intelligent guesses. So for making such intelligent guesses, visualizing the data often helps. So let us look at how to visualize the data. Let us get back to the notebook. Okay, so first is I am going to create a copy of my training data set. So I am going to look at only or I am going to visualize only the training data set and not the test set, because I do not want to unfairly bias myself on how the test set is distributed. That is sort of moderately cheating, right. So we don't want to do that. We want the test set to be completely different, and we do not want to bias our constructions of the model on the test set. So we are going to look entirely at the training set, visualize the data and see what parameters could be important, what features could be important, right. So let us now look at a simple way to plot. So let us say I want to just look at how the households or localities are distributed geographically. I can do that by just plotting a scatter plot with the latitude and longitude features, which is what I do here, and I see that localities that are distributed all over the state, it is not particularly useful, right. I can try to make this plot a bit better by adding some kind of transparency, right. So what this transparency does is it sort of allows me to identify which areas are fewer dots, so basically sparsely populated, and which areas are more densely populated. But again, this is not particularly useful. So let me try to make a really nice plot, right. So what I am going to do here is that I am going to create the size of each circle corresponding to the actual population in that locality, right, and I am also going to color each of these circles based on the median house value, right. And once I generate this plot, I see that now this plot is much more useful, right. So you see there are regions along the coast, I mean basically close to the big cities. So on the south here is Los Angeles, on the north here is San Francisco, and you see that very close to the cities you see big population centers and also population centers that are quite expensive, right, in nature. Whereas as you go farther inland into the state, you see that population is not quite high and the housing prices are also low, right. So this is quite useful to visualize, right. We can make this even more attractive, right, by superimposing this with the image of the California state itself. So I am going to download the image first. So this code block downloads the image, and then I am going to superimpose the plot that I generated before on this image of the California state. So this code block basically does that, right. So if I execute this, you see that we recover the plot that you probably saw a few slides before, right. So this is the state of California, and you see circles corresponding to population centers and colors of the circles corresponding to your median house prices, right, and we have made this plot look very pretty, right. So visualizing the data often helps, and it gives us a lot of visual cues. Let us now go back to the slides. Okay. Now the next thing that we should do is to look for correlations within the data, right. One important correlation could be median income. I mean we have already stratified our data based on income, and we created a stratified test split, right. And maybe another important parameter could be number of bedrooms, like typically if you have a small house like a 1 bedroom apartment or a house, that tends to be cheaper compared to an apartment with 10 bedrooms or a house with 10 bedrooms, right. So, so how important is are these two features, for example, and can we also create new features that can capture correlations a little bit better with the target variable. So we will try to create new features and then see how they look like. So let us get back to the notebook here. For looking at correlations among the features within our data set, this core function that is an inbuilt function within pandas itself is quite useful. So let us now execute that function, and once you execute or generate a correlation matrix, you can now define with respect to which variable you want to look at the correlations. We want to look at correlations with respect to the target variable. So our target is our median housing value. So let us look at correlations with respect to the target variable. So correlations that are closer to 1 or -1 basically indicate that your feature are strongly related to your target value, right. So 1 means that whenever your target value is increasing, your features are also increasing, or vice versa, whenever your features are increasing, your target values are increasing. If the value is -1, then they are anti-correlated. So if your feature values are decreasing, your target values are increasing, and this decrease and increase is perfect, right. So values closer to 0 indicate that your features do not really correlate with your target value. So it does not matter whether you increase or decrease the features, your target value may remain constant, right. So we do not want features that are close to 0, we want features close to either 1 or -1. And if you actually look at the features, right, it looks like median income is the most strongly correlated. So I think that was a good guess, right. So higher the income, higher the housing prices, or vice versa, right. And we also see a few features that have moderate sort of correlation, so or sort of weak correlation. One is total rooms, right, other is latitude, those have weak correlations. And the remaining ones, I mean housing median age also has weak correlations. The remaining almost have
almost zero correlation. So like longitude is like 0.04, that's not big. Total bedrooms surprisingly not big, right. So let's now try to visualize this correlation and see if we can gain something from it. So for visualizing I am going to plot, I am going to collect a bunch of scatter plots and then plot them in matrix form, right, and again pandas has a nice inbuilt plotting function to do this. So along the diagonal you basically see histograms because these are basically just plotting the distribution of the same variable, but if you look at the top row here, this is basically looking at how median house value is related to median house value itself. So that is why it is a histogram here, median income, right, total rooms and median age, right. So you see that with median income there is sort of roughly linear correlation, right. So as the income is increasing your housing prices are increasing. Total rooms surprisingly not so much, right. So you see a wide distribution of total rooms and the housing prices are varying all over the place, and same thing with median age, right. So all through the age categories you see housing prices being distributed, right, all through. So there is no real correlation between them, right. And you can look at correlations between, let us say sort of median income and total rooms also, right. So you can also look at correlations across the different features themselves, not just with the target value, okay. Let us now take a closer look at the median housing value, and we see interesting trends, right. So overall it is sort of linearly correlated, but you also see regions where it is almost horizontal in nature, right. So you see when the housing value hits the peak at 500,000, it is basically all over the median income, which is probably surprising, and it is probably because of noisy data or bad data collection, and sometimes we may have to live with that, live with noisy data. Let us now experiment with a few adding a few new features, and we are going to consider adding 3 new features here. So one is rooms per household. So if you look at our data set itself, it has total rooms and it has total households in a locality, right, but it does not have an attribute that says or a feature that says how many rooms are there on an average within a house, right. Maybe that is a better correlated with respect to your overall housing value or housing price. The second is bedrooms per room. So how many bedrooms do you have per total number of rooms that you have in a given locality, right. So the more bedrooms generally you expect the values to be higher, and also population per household, right. So how many people are staying on an average. So generally houses with larger number of people generally has lower housing value compared to lower number of people, at least this is the scenario in the US, it may not hold true in India. Okay, so we have added these 3 new features here. So the nice thing about pandas is that you can add new features or new columns in your data frame just by initializing their value, the column name, and then you can also do mathematical operations on the fly, right. So this is very similar to how we operate Excel sheets, okay. Let us now relook at the correlations with our target value of the median price, and we see that population per household fairly weak correlation, rooms per household decent correlation about 15%, right. Bedrooms per room is fairly reasonably strong or medium correlation, but it is also anti-correlated. So the more bedrooms per room you have, the lower is the housing value, right. So but at least it is about 25% anti-correlated. So so good. So we discovered couple of features at least that may improve if used within our model, may improve the model, right. We can also take a closer look at bedrooms per room, and we see moderately moderate level of anti-correlation. It is not very strong, but yeah, you generally see as the bedrooms per room increases, your housing value tends to drop, right. Okay, so we have now added these additional features within our overall data set. So we now see 3 new columns towards the very end, right, within our data set. And yeah, so that's good to go now. So let us go back to the slides. Okay, so we will summarize and sort of close this lecture out for now. So we basically defined a regression problem which was predicting median house prices in California. We defined our performance metrics, root mean squared error and mean absolute error. we tried out random and stratified split of data, and we went ahead with stratified split of data based on income categories. We visualized the data, understood some correlations with our target metric or target value, and we also introduced new features partially successfully, right. So in the next lecture we will now prepare the data for doing the machine learning aspects, and we will fit some models. So with that, thank you for joining in this lecture. I will see you all in the next one.